I'm going to try to explain how to interpret the pumping test data from Hanning Creek. Now, first of all, I'll try to explain the concept of what we're doing, and then I'll just try and explain the procedure without going through the maths. So essentially, we're talking about an unconfined aquifer here. Let's build an unconfined aquifer. So imagine that we have a slab of very impermeable material, and on top of that slab, we put a slab of sand, which is very permeable and porous. And we surround that on all sides with some water level that doesn't change, some fixed depth of water, and then maybe let grass grow on the top of it, and that's basically the configuration of the ground that we're talking about, or a simplified representation of that. If we look at a cross-section of this system, then we're going to see that there is a water table, and it's horizontal, and it's in equilibrium with the surrounding water bodies. So that is an unconfined aquifer because there's nothing stopping rainfall that infiltrates into the ground from reaching it. And it has a water table. So then we can drill a hole in the ground and put a pipe in the hole and put a well in the pipe, or in other words, put a pump in the pipe, and then we have a well. So there's our well in the middle of the aquifer. And we can also install one or more piezometers around the well, which we can use to monitor what's happening to the groundwater when we start pumping. And essentially that's what we have at Hanning Creek. So when you start to pump here, where we have water coming out of the well, you draw down what we call a cone of depression in the water table, which is radially symmetrical about the well. And the piezometer, this piezometer here, can be used to measure the drawdown as a function of time as we start pumping the aquifer, which is exactly what we did, right? So that's what we're doing conceptually. Now, if you come to the spreadsheet that you were given, we have this. First of all, we have our drawdown data. So this is time against the water level, and from the water level we can calculate the drawdown, okay, which is just how much the water level dropped from its initial value. And we can plot the drawdown, and you can see with time on the x-axis and drawdown on the y-axis, we see this curve that starts small and it gets rapidly bigger, and then it starts to sort of slow down. So that's the shape of a drawdown curve that we see, classic shape. Now, the speed at which this curve changes, or the gradient of the curve, is a function of the hydraulic conductivity of the aquifer. And the amount of drawdown that you get is also a function of the conductivity and storage of the aquifer. In other words, if you pump a different aquifer, you're going to get a very similar shaped curve, but the actual slope and the actual amount of drawdown will be different every time. But it turns out that, in fact, for an unconfined aquifer, we can expect that the shape of the drawdown curve will always match one of these lines, or it should always match one of these lines. And if we match it to these lines, then we can read off from the graph some values that will allow us to calculate our hydraulic conductivity, which is the objective of the exercise, right? So these are what we could call standardized or normalized curves. And the idea is to take our actual data, which I have here, and you have this spreadsheet, and to overlay our data, if I can do this, it's a bit fiddly, it's very fiddly actually, over the standard curves, and you want to, try to match these data sets to one another. All right, so I'm not going to do this properly, but you would basically jiggle this around until you thought, oh, that's the best fit I can possibly get. Now we're going to focus on the early time fit, in other words, the fit to these first few points here first, and then in B we'll do the late time fit. So in B you can try and do the same thing, but this time you're going to focus on how the later points match the curve. Now make sure that the curve that you fit with the late and early time is the same color. So maybe I'm using the orange, for example. Okay. Now, when you've done that and you've got your fit, and by the way, you don't have to get this perfectly. This is a rather subjective process, and you'll all probably get different answers, and that's absolutely fine. Anyway, but when you've done it, there's some certain things we need to record. So first of all, we need to figure out which line we're fitting. So here I might be fitting this orange line, which is 0.06, and so I'm going to go to my calculation sheet, and in this thing, this funny gamma thing, I'm going to put 0.06. Okay, so that's matching the number in the legend up here. Then I'm going to map some fixed point on both axes. So what I need to do is I've got this point A here, and it's located at W equals 1, and 1 over UA is equal to, if I read up here, 10. Okay? So I need to go for the early time. Early time, this was 1 and this was 10. All right? So I need to make sure that that's 1 and 10, and if it's something else, you should write those in. And then I'm going to read off that same exact point, but on the other axis. So this is now my time axis, right? So this point, if I follow it up to the time axis, it's just past 10 minutes. That's 10 minutes is there, 20 minutes is there, so I'm going to say that's about, I don't know, 12 minutes. So I need to put time early is going to be 12 minutes, or whatever you want to call it. And then take the same A point and read off the drawdown. So it's coming along this line here, this line here, this line here, which is, so what's that? This is 0.1, this is 0.09, 0.08, so it's 0.07. So I'm going to put for my drawdown early 0.07. Okay, then you're going to do exactly the same thing for the late time. This time we have point B, so make sure you get the points WB, 1 over UB for the first bit, and then time and drawdown for the second bit. Put all your numbers into the spreadsheet. Don't do anything else. Don't overthink it. And this thing is going to spit out some numbers here. I'm particularly interested in the horizontal hydraulic conductivity. And so that's the result that you're looking to get and to interpret in your report. So that was a bit of a quick explanation of the process for doing this and what you're trying to achieve without going into huge detail. Hopefully that's sufficient to get this assignment done. Good luck.